Okay, so Friday you've got the homework due before class, and we'll have the exam during class. You don't need to bring your computer. It's just going to be problem solving on the paper. I'll provide the equation packet, so no need for you to prepare a notes page. And then the next phase of the design project, that's the one where you're sizing the reservoir. That's due Wednesday of next week. And in the previous lecture, I showed you where there's a recorded demo from several years back where I step by step go through the process of showing you how you calculate the incremental volume stored during every hour. The assumption being that you start off with an empty reservoir, you look at the difference between the inflow and the outflow for every hour, and then you say, you know, during this hour, how much came in, how much went out, how does that compare to like the last hour, like how much was already in the reservoir at a given time, so is the water level going up, going down? So that procedure just basically identifies the maximum volume that needs to be stored. So you've got that due Wednesday of next week. Does anybody have any questions before we start talking about spillways and weirs? All right. Well, if you do have questions as you're reviewing for the exam or solving the homework problem, just let me know. I've got office hours today. I'll be in the office for most of tomorrow, so let me know how I can help. This is a map that shows the inland waterways of the United States. And we're pretty familiar with the idea here in Huntington that rivers can be used as a means of transportation. And in fact, it's a very efficient way of moving heavy bulk cargo from place to place because it uses so little fuel to push a barge up or even down or up the river compared to other transportation methods. Like rail is about 10 times more efficient from a fuel standpoint than trucks are. But then pipelines and river traffic is even, it's not 10 times more efficient than rail, but it is like 3 or 4 times more efficient than rail in terms of the amount of fuel that gets used. And so here in the United States, we have almost a perpetual economic advantage compared to a lot of other countries that don't have the overlapping of this really efficient transportation network with highly productive agricultural regions. You know, some countries don't have either. Some countries aren't able to produce their own food and they don't have effective transportation networks. But we have both overlapping, which means that in the United States, we're able to get agricultural products like wheat, corn, soybeans, beans, from areas that are hundreds of miles away from ocean-going ports. Those products can be loaded onto barges and taken down the river and then sent out to market from there. So it's really an incredible stroke of fortune that we've got available here in the U.S. One of the river networks, relatively smaller compared to the Missouri or the Ohio or the Mississippi River network, but the Columbia River system in the western part of the United States connects Oregon, Washington, Idaho. It goes up into Montana, Wyoming, and into parts of Canada as well. And so you're probably familiar with the fact that in Idaho they grow a lot of potatoes. In Washington and Oregon, they're both highly involved in agricultural industry, and so it's a great way to get those food items to market. But also, it's an important source of electricity for the region because they have a dam on the Columbia River, the Grand Coulee Dam. It has a rated maximum power generation capacity of 6,809 megawatts. And it's hard to put that into perspective. I mean, if you're not familiar with the megawatt, then, is that a lot? Is that a little? Well, just as comparison, the John Amos power plant, which is in Winfield here in West Virginia, has a rated capacity of 2,933 megawatts. And that is the largest coal-fired power plant in the AEP inventory. And AEP is a big power company. They have a lot of customers. They sell a lot of electricity, and John Amos is their biggest power plant. John Amos provides enough electricity for more than 2 million households. So this Grand Coulee Dam could provide enough electricity for more than 5 million households. There's something called the capacity factor, which kind of compares the maximum electrical power capacity to an annual average of how many kilowatt hours or megawatt hours they actually end up producing. And long story short, not every turbine is operating every hour of the entire year. Certain turbines are taken offline for maintenance. Sometimes the water levels aren't high enough to generate at the maximum power capacity. So in the case of the Grand Coulee Dam, they're not operating at 6809 megawatts all year long. They're operating on an annual average at about 36% of that. But still, it's an amazing resource, and that electricity is very valuable and has helped to fuel the economic growth in Portland, Seattle, and the entire Pacific Northwest. So we're going to be talking today about the hydraulics of water flowing down the spillway. Water gets through a dam in many different routes as it ends up. There's typically one route that the water flows through to generate electricity, and that's separate from this overflow spillway. The spillway isn't generating any electricity because all of the energy is just being wasted as the water flows down over the front face of this surface. In order to capture the energy, you have to produce pressure, and so there's something called a penstock, or it's a big, large diameter pipe that at one end has a turbine that's spinning around, and so we don't see those. I think that this might be where the water's flowing to generate electricity. And then oftentimes there will be separate routes for the migration of fish in newer dams where they've built them with a little bit more appreciation for the need to allow migrating fish. They'll have fish ladders or sometimes really sophisticated like fish vacuums that will suck water from downstream and kind of like deposit them upstream. Kind of an amazing thing. But dams are really interesting. There's a video that I'd recommend that is relatively new to YouTube about how all dams are temporary. And anybody have an idea of why all dams are temporary? If you think about what this structure is doing, why does it have a finite lifetime? Sedimentation, yeah, because there's runoff that this water comes from storms, right? The hydrologic cycle is driven by the sun, which evaporates water from the ocean, gets into clouds, it rains onto the soil in the watershed. Let's look, this this brown area is the contributing watershed for the Columbia River. So in theory, any raindrop within this dark shaded brown area could end up at the Columbia River. In practice, some of the raindrops are going to evaporate again. Some of the raindrops maybe are infiltrating into the soil and replenishing groundwater, but this contributing area all feeds into the outlet of the watershed. And so when there's heavy rainfall, it takes some of the loose topsoil with it, and we see that here in West Virginia. And when we look at the Ohio River, sometimes it looks like murky, just like maybe a little bit gray, a little bit bluish. It's never like crystal clear. But after heavy rain, you can see it's like chocolate brown. The appearance changes based on how heavy it's been raining because it takes sediment with it. And so there's soil in the water, and eventually the soil is going to be trapped behind the dam because the water velocity becomes much slower in the reservoir immediately upstream of the dam. So when the velocity slows down, the soil particles settle downward. They don't have enough mixing energy to keep them suspended. And it's just simply not practical to dredge all of that soil out. It's very, very expensive. And so in the long term, the storage capacity behind the dam will decrease, and it'll generate progressively less electricity. It will have progressively less storage capacity for the irrigation potential, and it'll have to be retired. And there are a number of dams in the western part of the United States that have been torn down, where they, about 100 years old, they're full of sediment, they're realizing the environmental impact that they have on fish movement and other aquatic life, and so they've just completely removed them. So it's kind of an interesting topic, dams. Here's just another look at that big spillway, which normally would be used in periods of high water flow, where they're not able to send all of the water through the turbines that's coming into the reservoir. When there's more water coming into the reservoir than can be reliably used in hydropower scenario, then they would open up some of the gates at the top of the spillway and then allow water to flow down the front surface. And this is what it looks like when they open up that gate. The water's picking up a lot of energy as it falls down such a steep surface. You can see it's all white simply because of the velocity of the water. But let's watch this video, which describes a little bit about the hydraulics associated with weirs. That same YouTube channel, as a matter of fact. Practical engineering.
A weir is a small dam built across.
So for those of you who are going to the water treatment plant today, we'll also see a similar thing where they try and increase the weir length in clarifiers for the flow off the top of a clarifier. You could have water flowing around off the top of a clarifier, and you'd have the circumference of a circle like this. But if you have I'm not sure exactly in Huntington whether they do it, but in some places they could have a bank of additional sharp-crested weirs going into the flow like this, and so now instead of just the circumference, then continuing that on, you'd have all of this length for the weirs, and so just extending it into the water, increasing the length that water can flow over, both reduces the height of the water as it goes over and also reduces the velocity for the discharge, which is the main benefit in a clarifier. All right, so we saw an equation in that video which was saying that the flow over a weir depends on the length of the weir, the height of the water above the weir, and then there are some factors which we wrap a couple of different terms into a discharge coefficient, and typically it would be the gravitational constant as well as a factor that talks about energy loss over the weir. So if we look at water flowing over a spillway, so it talked about the nap is the shape that the water would take if it was flowing over a sharp-crested weir, and we try and simulate that shape both because it increases the efficiency of flow and also it enables us to, in some sense, react to higher or lower flow rates by maintaining a more constant head level. It increases the pressure at the spillway crest when the water head is lower, and so that would cause the tailwater, the water upstream of the spillway crest, to be higher than artificially higher than it ordinarily would be. So there's in this shape of an OG spillway, there's kind of an important reason why we follow that shape. So here you can see that we're measuring two different things. There's a hypothetical sharp-crested weir, and that's what is shaded here in the darker gray. And so we can either express the flow rate over this spillway as the relationship between the hypothetical sharp-crested weir or the actual OG spillway and the applicable discharge coefficient for that, and then the elevation above the top of the spillway crest to the water level versus where capital H here is from the hypothetical sharp-crested weir. H sub D is the height of the actual physical water elevation above the spillway crest to the water upstream. So an OG spillway is just kind of this idea that you can flatten out the rating curve, and the way that it does it is because at the design flow rate, you'd have atmospheric pressure at the top of the spillway crest. Because as the water is flowing over it, it's picking up velocity. And so normally, under static conditions, then the pressure of the fluid at a given depth is just the distance, the depth itself multiplied by gamma. But the pressure here on the spillway crest, it's not static conditions. And so the pressure is lower on the spillway crest than ordinarily it would be because the water has accelerated and it's got velocity now. And so you could say that there's a Bernoulli effect happening where there's some exchange of potential energy upstream of the spillway that's been translated into kinetic energy. That acceleration, increase in velocity, decreases the pressure. So at design conditions, you've got actually a atmospheric pressure at the crest of the spillway. But then when the flow rate is lower than that, that means that the velocity is less going over the spillway. And so you'd have a positive pressure at the spillway crest, which actually reduces the flow rate and increases the depth more than it would be if it was just a sharp-crested weir. And then the reverse is true above the design flow. Above the design flow, then the I'm sorry, I might have said that backwards. Above the design flow, the pressure at the crest is negative, whereas when the design flow is less than, when the flow is less than the design flow, then the pressure is positive. So basically it's acting as a non-moving reaction to the flow. So in the video we watched, it showed how the gates could be raised or lowered to artificially increase or decrease the resistance of flow over the spillway crest. So this is just a passive way of doing that, of accomplishing the same thing. The flow over the spillway crest is a little bit faster and easier than it ordinarily would be at the higher head level because the pressure is reduced. So let's actually practice using these numbers here, and because we've got the traditional units, we're going to use this formula here, which is, the coefficient of 3.97 is specifically for traditional units, where we're using 32.2 for G and so on. The spillway length is the distance into the page. That's L. The parameter here is 300 feet. And let's say that for a 100-year storm, which means it's got an average return period of 100 years, or the probability of us seeing this storm in any given year would be 1%. So we want to find out what is going to happen to the water level upstream of the spillway when we're trying to put 38,000 cubic feet per second over the spillway. So 38,000 cubic feet per second is the Q, and we know the length of the spillway, and we just want to know what is the water depth going to do as a reaction to that. So if we know that the water level can't be any higher than 4,350 feet, and that may be because of bridges that are in the area over the tributaries. It could be that there are buildings along the shoreline of whatever river or reservoir is in this area, but we just know that we don't want the water level to go any higher than 4,350. So what we're trying to figure out is what should be the elevation of the spillway crest. And so the water level minus H sub D will tell us the elevation of the spillway crest. So let me pause for a second and give you a moment to calculate both the elevation of the spillway crest, but then also, like this theoretical weir crest, it's sometimes also important to know where that's at. So we'll look at that as a secondary question as well. Okay, so we're just going to rearrange this equation to solve for h sub d. We want to know how high above the spillway crest is the water level. And so to solve for h sub d, we've got a flow rate of 38,000 CFS, weir length of 300 feet. We take all this to the 2/3 power. So the water depth is going to be 10.06 feet higher than the spillway crest. And so that means if the spillway crest has to be below 4350, we should put it at 10.06 feet below 4350. So that means that the elevation of the spillway crest should not be higher than 4339. Now the theoretical weir crest, we would just solve the equation for h and then do the same process of subtracting h from the given elevation. And so this theoretical weir would be even lower than the spillway crest. Now, you're not actually going to build the theoretical weir, but it's useful to know that from the perspective of other equations which are related to the velocity of the flow and so on that depend on the theoretical weir height. So that's a spillway, and the video that we watched just talked about weirs in general. And this gives you an idea that as the water is flowing over an obstruction, there's actually not just a single depth. You know, we talked about how when an obstruction gets progressively deeper and deeper, that the water flows at the critical depth over the obstruction. But there's multiple things happening in a weir this short, because not only is the water going to be flowing at the critical depth over the obstruction, but then also the water is being drawn down as it flows over the edge of the weir. So there's an acceleration where the water depth is decreasing briefly as it approaches this overflow. But broad-crested weirs are used to measure the flow. They're not necessarily used to regulate the flow, but the idea is that if we put in some obstruction that's higher than the maximum step height that can be tolerated without inducing pooling, that the water would pool upstream and it would flow at the critical depth over the obstruction. But even though it pools briefly upstream, when we introduce this obstruction, the flow rate Q isn't changed. It's just flowing at a deeper depth than it ordinarily would have without the broad-crested weir. So you'll notice here in this diagram it's showing that the energy grade line is the same regardless of whether we have the weir or we don't. But then this is just saying that we measure some height, the height above the weir up to the energy grade line. And so here H is the specific energy. Because remember, specific energy is the depth plus the velocity head. And so this energy grade line is, the velocity head is the gap between the water depth and the energy grade line. So they're picturing it here prior to the critical flow, when the water accelerates and flows at the most efficient depth over the obstruction at the critical flow, then relatively speaking, more of the energy would be wrapped up in the energy grade line. And by the way, this is not to scale, because remember, what we've already learned is that when we have a rectangular channel and the water's flowing to critical depth, that the velocity head only represents 1/3 of the specific energy. So broad-crested weirs work by forcing critical flow over the obstruction. And it's good for us to know that it's critical flow, because if we know that the flow is critical over the obstruction, then we can very easily measure the flow rate. There's this approach to measuring the flow rate, and then there's also something called a flume. And honestly, flumes are used more often than broad-crested weirs as a means of measuring the flow rate, because this has a big disadvantage. This weir, well, two disadvantages actually. One of the disadvantages is just that there's energy loss as the water flows over the obstruction. whereas if we use a flume, the energy losses are less, very minimal. And then the other big disadvantage of a broad-crested weir is the same thing, the same disadvantage as a dam, where you can have the accumulation of sediment and trash and debris upstream of the weir. And so it can become clogged. It requires maintenance. So here are the formulas that describe the flow relationship over a weir. And so there's a discharge coefficient, C sub D, related to the energy losses. And then there's also some constants here related to, for example, the gravitational acceleration, and then the 2/3 H here represents the critical depth. We know that when conditions are critical over a broad-crested weir, they'll be critical. Then we could replace 2/3 H with the critical depth itself. And so the advantage of having a broad-crested weir is just you measure the flow depth, take it to the 3/2 power, multiply it by G. B is the width of the weir, same as it was before with the spillway. And then C sub D is some discharge coefficient that relates the energy losses as a function of how tall the weir is, H sub W, relative to the specific energy over the weir. So this formula allows you to estimate the discharge coefficient given the specific energy and the height of the step. So this is a broad-crested weir, and this is a sharp-crested weir. We've already talked about sharp-crested weirs a little bit. If we were going to compare the energy at 1 and the energy at 2, and specifically if we measured the energy above some datum where the datum is set at the elevation of a sharp-crested weir, then at 1 the water has elevation and velocity head. At 2, if we set 2 to be at the same height as the datum itself, then it wouldn't have any elevation. So y2 would be 0, but it would have some additional velocity. So the extra energy that was previously tied up as elevation is being transferred into additional velocity at 2. So if we say that y2 is 0, then this formula would allow us to figure out what is the velocity at 2, the added velocity that came from the water being drawn down as it approaches the sharp-crested weir. And this is actually very similar to the discharge from an orifice, the equation that we've seen before, the square root of 2gh, because the height of the specific energy here is partly elevation above the datum, so the water depth, and partly velocity head. And so we can combine those two terms, and most of the energy upstream of the sharp-crested weir is the depth itself, but strictly speaking, H is the specific energy there, and so we could calculate the velocity of the flow with that. A suppressed weir, this terminology is important. A suppressed weir is when the location of the overflow is the full width of the channel. And let me just show you, let me jump ahead for a moment and show you an unsuppressed weir, because you don't really appreciate what a suppressed weir is until you see one that's unsuppressed. And so this is an unsuppressed weir. So this rectangular shape is like the width of the channel. So if we had a river that's flowing, this is a top view. So here's the water flowing from a river, and so then the water's flowing over the edge here. So if the river channel is very wide, but the width of the weir is less wide than the river, then that's contracted or unsuppressed. So this, suppressed, it means that the water's flowing over the entire width of the channel. So in the case of a suppressed weir, these are the equations that would allow us to relate the flow rate over the weir with the height of the water and the length of the weir. And then here you can see that there's the discharge coefficient C sub D, which is related to energy losses, drawdown, contraction losses, and so on. And then we've got a couple of constants. Ordinarily, as long as the height Z, the height of the weir itself, is significantly more than H, then we can just assume that the C sub D is about 0.62 if we've got the height of the water is small relative to the weir height. And so if the ratio, like if the height of the water is about 10% of the weir height or less, then the discharge coefficient becomes 0.62, and then lumping all of these constants together, where C sub D is this 0.62, 2/3, the square root of 2g, then some C value times the length times H. And now this is the formula that you saw in the video. And he said that you can sometimes see C values as high as 4, depending on if you're using an OG spillway rather than a sharp-crested weir. So this is for a sharp-crested weir, where you're going to have a discharge coefficient of 0.62. If you use an OG spillway, then that brings the discharge coefficient higher, and then lumping that discharge coefficient with 2/3 and square root of 2g, you could take the C value much higher than 3.32. But this is for, remember, the sharp-crested weir. The suppressed weir, we would just account for the suppressed weir, which is the full width, is the physical length of the channel, and the length of the channel would be, well, its width actually, what we would call the width of the channel, and then here is the length of the weir. So the length of the weir is, what fraction of the channel's width is the water flowing over. And if it is suppressed, those two are equal. If it's unsuppressed and the weir width is contracted compared to the channel width, the way that we react to that is we calculate L prime and use that in the weir equation instead of L. And so L prime just accounts for some ineffective flow area around the edges of the weir. And so typically what you do is you subtract 20% of H, where H is the height of the water as it's flowing over the edge. So that's it for the material that's going to be included in Exam 2. Exam 2 is going to be lectures 20 through 30, so up to and including spillways and weirs. Make note of today, 11:44. I'm letting you out 6 minutes early. I think that's going to cancel out all my previous debts of 1 minute here, 1 minute there. So I'm finally back in the black. All right. So I'll see you on Friday for the exam.